Let's start this section with a little review. Given a quadratic function, remember a quadratic function takes this form, ax squared plus bx plus c, where a, b, and c are real numbers and a is not zero. If we have a quadratic function, how many zeros can that function have? Now remember, zeros is the same thing as the roots of a function, which is the same thing as the x-intercepts of a function. So what I'm asking is, how many x-intercepts are possible? Now we learned several different techniques to find the zeros of a function. What we did each time was we set the function equal to 0 and we solved for x. Now, if the function was a function that was easy to factor, then we would factor the function, we would get the roots really quickly. Another thing we learned was we could use something called the quadratic formula, and that would give us the roots. And we can also graph this. We can graph this function, just see where we cross the x-axis. So how many different roots were possible? How many different numbers did we get when we solved for x? So every time we did this, we talked about real zeros. Or in other words, real roots or real x-intercepts. And what I mean by real zeros means on the real line. What real numbers such as integers, square roots, irrational numbers, things like that. But what kind of value could we get for x that was a real number? So we had three options. We could have no roots, so no zeros. We could get 1 0 or 1 x-intercept, or we could have 2 zeros when we factored this, or we used the quadratic formula, or we graphed it. For example, maybe it would be easier to give you some examples. Let's say we had y is equal to x squared. If we set this equal to 0, we can factor this, and we can also just take the square root, and we get plus minus square root of 0, so we get x is 0. So here we have one real root. So you can see that it was possible to get 1 0. And we could graph this function here, this x squared. This is a parent function we learned, and we can see that when we have 1 0, which it means one intercept, x-intercept, that the vertex is that x-intercept. And the vertex is touching the x-axis. Of course, you could flip this upside down. You could have a function like this. It would have 1 0 as well. So when you have 1 0, that means the vertex is touching the x-axis. Okay, when we have 2 zeros, we would have something like x squared minus 9 is our function. So let's say y is equal to x squared minus 9. You can see that we could factor this. This is x minus 3, x plus 3. And so our 2 zeros are 3 and negative 3. And if we were to graph this one, I'm going to just graph it here so I don't have to draw another plane. This is x squared, the parent function, which was the function we just looked at, shifted down 9 units. So if we were to graph it, it looks something like this, and you know that you cross the x-axis 2 times. So we have 2 real zeros. Now, if I gave you something like, let's put this one in red, y is equal to negative x squared minus 4. You could try to factor out this negative. You'll get x squared plus 4. Set it equal to 0, and you can divide by that negative, and you get x squared plus 4. And this is not factorable. And if you use the quadratic function for this, the quadratic formula, you'll get a square root of a negative number. So we can even use the quadratic function. Just so you can see what I'm talking about. We'll get, so here we have x squared plus 0x plus 4. That is our function. You can see this, we factored out this negative. You could also put a negative in front of everything, but you're going to get the same answer. So b here is 0. So we get 0 plus or minus the square root of 0 minus 4 times 1 times 4 over 2 times 1. And what you'll see is you get the square root of negative 16. And what we learned is if we got the square root of a negative number, then we say it has no roots, so 0 real roots. And also we could graph this. So if we graphed this function, so this function is negative x squared minus 4. So let's remember how we graph this. So we have the parent function, which is x squared. We can move the parent function up 4 and then flip the graph. So negative, let me write this function here. This function y is equal to negative x squared minus 4. It looks like this. And how I got this was I took my parent function x squared, I moved it up 4, and then I multiplied that by a negative. And what happens is when you multiply by a negative, it flips the graph down. So the graph looks like this, and why I'm graphing this is because you can see it doesn't cross the x-axis, which means you don't have a real root because this is a real number line. So the options were, we either had no real roots, 1 real root, or 2 real roots. And notice I'm saying the word real each time. Before I never really talked about real roots because there are imaginary roots. So what's going to happen and what we're going to learn in this section is that if you have no real roots, you're going to actually have 2 complex roots, which are going to be imaginary roots. So to prepare us for that, we need to talk a little bit about complex numbers. What is a complex number? So a complex number takes this form, a plus bi, where a and b are real numbers. And I is equal to the square root of negative 1. So before we never really talked about square roots of negative numbers. Now we're going to talk about them. So imaginary doesn't mean they don't exist. That's just what we call them. We say they're imaginary numbers, but they're real numbers. And when we say real numbers here, like we're talking about, so let me put it here. Real numbers are things like -1, 0, 1, -30, 2.5. So you've got integers, you've got the zero, you've got fractions, you've got decimals, square root 7, pi, irrational numbers. These are real numbers, and they all live on the number line. So when we draw a number line, so we put 0 here and 1 here, a half is a real number, and it lies in between 0 and 1. The square root of 2 is a real number, and it lies between 1 and 2. So square root 2 is somewhere in here. So all of these numbers are real numbers, and they live on the number line. Complex numbers actually contain the real numbers. It's a bigger set of numbers. So let me give you some examples of complex numbers. So something like 5 plus 2i. You can see that this number and this number belong to the real numbers, just like this definition here. A real number takes this shape, a plus bi. So I have a number plus a number times I, where this is a real number and this is a real number. And we call this piece, the part without the I, the real part of the complex number. and we call this the imaginary part. Another example would be something like 3.5 plus pi I. Notice that this number and this number, they're both real numbers. And we have a part that's real, that doesn't have an I attached to it, and we have a part that has an I attached to it, and that's the imaginary part. Okay, another example would be something like this, just the number 12. Why is this a complex number? Because 12 is the same thing as 12 plus 0 times the imaginary number, and 0 times anything is 0. So the imaginary part goes away, which tells us that the complex numbers contain the real numbers. We could also have something like negative 2i, which is 0 plus a negative 2i. So we have that the real part of the number, the complex number 0, which we don't have to write the number 0, we just get the imaginary part. So complex numbers look like this, look like this, and look like this. You have a plus bi, a and b can be 0, and or any real number. Okay, so the next topic is, I mentioned that we've been studying real roots. We're going to start talking about complex roots. And complex roots exist with quadratic functions that don't cross the x-axis. So how do we find complex roots? Let me give you an example of a function that has complex roots. So f of x is equal to x squared plus 1. Okay, if we wanted to find the roots of this function, we set it equal to 0. And you can see I'll move the 1 to the other side and I'll get x squared is equal to negative 1. So we're squaring a number and we're getting a negative. Previously, we would just say there's no solution. And when I said no solution, what I really meant was there's no real solution, which means there's no real number that we can plug in for x to square it and get a negative. And that's what your calculator will do as well. If you took the square root of both sides, what would happen is you put square root negative 1 into your calculator, the calculator will say error or something like that, because what it's returning are real numbers. And there's no real number, like I said, that when you square it, get a negative. So this is not a real number, it's a complex number. So whenever you see the square root of negative 1, that is going to be I. So the solutions to this function here, there are no real solutions, but there are two complex solutions. And those two solutions are x is equal to I and x is equal to negative I. So whenever you have no real solution, you're going to get two complex solutions. When you have one real solution, then that solution is going to have a multiplicity of 2, meaning that when you factor the function, that will show up 2 times in your factored form. And if you have 2 real solutions, then you're not going to have any complex solutions. And when you have 1 real solution, you're not going to have any complex solutions. The only time you have complex solutions is when there are no real solutions. That's when you get 2 complex solutions. And before we said this was not factorable, but it actually is factorable over the complex numbers. This factors into x minus I and x plus I. And what happens is if you want to double check that this factorization is correct, you FOIL this. And if you FOIL it, you'll get x squared minus I squared. And since I is the square root of negative 1, if you square this, you'll get negative 1. And so this is equal to x squared minus a negative 1, which is x squared plus 1, because you can switch these. So this is really a crash course in complex numbers here, like a crash review. We're not going to do too much with this. What we're going to do we're not really studying the complex numbers so much, but we want to at least have seen them, and we want to talk about finding complex solutions. Okay, let's move on. Another thing I want to mention is something called a complex conjugate. So if you have a number that's a complex number, a plus bi, the complex conjugate of it is a minus bi. So for example, 2 plus 3i, the complex conjugate is 2 minus 3i. And if you want 2 minus, if I give you 2 minus 3i, you would tell me its complex conjugate is 2 plus 3i. So these are complex conjugates. So you just switch the sign of the imaginary part. Okay? Now the reason we're talking about this is because when you find roots of a quadratic function and there are no real roots, I mentioned that there's going to be 2 complex roots, and it turns out that the complex roots are complex conjugates. So if you have one of the roots is 2 plus 3i, then the other one is going to be 2 minus 3i. So let's do some problems where we find the complex conjugate. So I want to find the complex conjugate of the following. It looks like I have 7 problems. Maybe write these 7 problems down, pause the video, and watch me do a few of them and try to find some yourself. And then you can double check and see if you got the right answer. Okay, 3 plus 2i. What's the complex conjugate? Now I'm going to put the complex conjugate in blue. So the complex conjugate is 3 minus 2i. For 5 minus 7i, what is its complex conjugate? Well, it's 5 plus 7i. For negative 3 minus square root 10i, what is its complex conjugate? It's negative 3 plus square root 10i. Okay, the next few problems tend to confuse students, and what I suggest you do is you write it in the expanded form of a complex number. Here I have 4i. This is the same thing, let me do this in black, as 0 plus 4i. Okay, and that usually helps people figure out what the complex conjugate is, because you switch the sign. So you're going to get 0 minus 4i, and you can just say negative 4i is its complex conjugate. Here I have 3 more numbers. Negative square root 3i, its complex conjugate is square root 3i. So I change the sign of the thing in front of the imaginary number. Okay, here I have 12. What do you think its complex conjugate is? Well, 12 is the same thing as 12 plus 0i, and we switch the sign here. So we'll get 12 minus 0i, but 0i is the same thing as just 0. So the complex conjugate is just 12. And the same thing here, 0 is 0 plus 0i, so the complex conjugate is 0 minus 0i, so just 0 is the complex conjugate. So the complex conjugate of a real number is itself. And the complex conjugate of an imaginary number, you put a negative with that. So imaginary number would just be this piece of it. And you could also, when you have something like 12 plus some number here, you switch that positive to a negative. Okay, I think we're ready to start finding complex roots of a function. So here I'm going to give you, I think I have 6 functions. In fact, I'll scroll down, and what you can do is you can write each function down, give yourself a little space to put a graph and to write some information down. And then you put 6 problems down. Maybe watch me do 1 or 2 and see how many you can do, and then just check and see if you get the same answer. So the first problem is f of x is equal to x squared plus 3. The second problem is g of x is 4x squared minus 9. Then we have h of x is x squared minus 2x plus 5. Followed by k of x is negative 2x minus 4 squared. F of x is x minus 3 squared plus 2. And I think this is the last one. G of x is negative 3x squared plus 6x plus 1. Yeah. So let me scroll back up. We're going to do these 6 problems. And the directions say we want to find the following functions, we want to determine the character of the zeros. So the first thing we want to do, which means figure out if we have 0, 1, or 2 real roots, and if we have 2 complex roots. After we determine the character of the zeros, we want to find the zeros, and then we want to graph the functions. Okay, let's work with the first one, x squared plus 3. Looking at this function, you can look at the right-hand side and you can go ahead and see that this is going to have 2 complex roots. Why do I know that it has 2 complex roots or 2 complex zeros? Well, if I set it equal to 0 and I move that 3 to the other side, I get something squared as a negative. And there's no real solution to this. We can't square something and get a negative 3. I also noticed, because I've done a lot of factoring, whenever we have something plus just a number like this, there's no there's no real solutions. We can't factor it. And when you can't factor it, you don't have a real solution. You could also just go ahead and graph this. This is very simple to graph because this is the parent function x squared and with a 3 on the outside, which means we move that parent function up 3 units. So it looks something like this. And just by graphing it, you can see you don't cross the x-axis, which tells me we don't have any real solutions. And if we don't have real solutions, we have 2 complex solutions. Okay, now we want to find the complex solutions. We have determined the character and we've graphed the function because that was really easy. Now let's find the zeros. And we're almost done with this problem. We've got x squared is equal to negative 3, so we take the square root of both sides. Okay, let's do that. That gives us x is equal to, remember when you take a square root, you always get a positive and a negative. Square root negative 3. All right, this square root breaks into the square root of 3 times the square root of negative 1. Whenever you have the square root of negative 1, you're going to cross that out and make it an I. So x is equal to plus or minus the square root of 3i. Those are our 2 complex solutions. X is equal to square root 3i, and this I is not underneath that square root. And x is equal to the negative square root of 3i. Again, that I is not under the square root. So here are your 2 complex solutions. And look, they're complex conjugates. Okay, I also want to mention how would we write this in factored form. Now you don't have to do this, but I'm going to do it just so that you've seen it. You can factor x squared plus 3. This factors into x minus square root 3i and x plus square root 3i. And you can FOIL this out and you can see that it'll end up being x squared plus 3 because you get x squared and then you get a minus square root 3i and with a plus square root 3i, those cancel. And then you'll square these 2 pieces by multiplying them. So let me just write it out. So you get x squared plus square root 3ix minus square root 3ix. I'm just foiling. Minus square root 3i squared. This one times this one, this one times this one's here, this one times this one is here, and this one times this one is here. These 2 cancel out because I have a positive and a negative. And then when I square this, remember, if you square 2 things being multiplied together, you could just square each piece. The square root of The square root of 3 squared is just 3. And then I squared is -1. And that cancels out this negative. So you get x squared minus square root 3 squared times I squared, which is x squared minus 3 times -1, which is x squared plus 3. So whenever you have x-intercepts, you can write it in this factored form. I'm only going to do it for this one, just so that you've seen it before, in case you ever see it again in, later on and if you take calculus. Okay, let's move on to the next problem. So I have 4x squared minus 9. I want to find the complex or real roots. I want to determine how many I have, and I want to graph this. So first, to figure out the character of the roots, I'm going to set this equal to 0. And what can I do? Well, I can move the 9 to the other side and divide by 4, and that'll give me x squared, right? Notice that I have a positive number on this side. And to find the roots, I would just take the square root, right? And this is a positive number, so I'm going to get 2 real roots. I could also use the quadratic formula, and we're going to do that a little bit later. But just looking at this, I can see that if I take the square root, like that, I get x is equal to plus or minus 3 over 2, because I break the square root. The square root of 9 is 3, and square root of 4 is 2. So I'm going through 1.5 and -1.5. So let's put some dots here. So this is 1, -1, so this is -1.5, and this is 1.5, because 3 over 2 is 1/2. And we could also graph this by transformations of functions. We start with x squared, and then we multiply it by 4 and move it down 9, which tells me if I have x squared, multiply it by 4, I stretch the function. And then I move it down 9, I can go ahead and figure out where this vertex is. It's way down here. And this function, we've done graphing, so I'm not going to spend too much time on this. I'll do my best to draw quadratic. It looks something like that. And you can see that this looks a little stretched out. The vertex here is 0, -9. And you can find the vertex by using that formula. The vertex is -b over 2a, and plugging that in to your function. Notice that the b term here, because 4x squared minus 9 is the same thing as 4x squared plus 0x minus 9. -b, well, that'd be -0, and 0 divided by anything is going to be 0. So that's where I got the first one, 0. And then if you plug 0 into this, you get -9. And you can see that corresponds to this vertex, 0, -9. And the function is pointing upward, just like this. So we found the zeros. We have 2 real zeros. And we found the graph. Let's move on. We have h of x is x squared minus 2x plus 5. So we look at this function and we say, oh, can we factor it? So let's set it equal to 0 first. Is it factorable? Well, what I like to do to try to figure out if something's factorable is I say 1 times 5. Can I find 2 numbers that multiply to give me 5, add to give me -2? Well, 5 and 1, that's the only way to factor 5. And if you add them, you get 6. You can't get -2. Okay, so this isn't factorable. So what I'm going to do is I'm going to use the quadratic formula. Now, we need to mention that in the quadratic formula, let me write it down. This is the quadratic formula. Okay, how you can tell if you have a real root or if you have complex roots is by this piece right here. Let's focus on this piece, because if we're going to have a square root of a negative number, is going to come from this piece right here. So let's write a few things down. If b squared minus 4ac is greater than 0, what's going to happen is we're going to get two real roots, and they're not equal. Why wouldn't we get just one root? Because we're going to have negative something plus that number, and then negative of something minus that number. So we're going to get two different numbers here. If you have b squared minus 4ac is equal to 0, then you're going to get one real root, and it's going to have a multiplicity of 2. That means if you factored it, it would show up 2 times. But all you really need to know is that you're going to have one real root. When you run into trouble, when you get complex roots, is when this square root, what's underneath, is less than 0. You're going to have two complex roots, and they're not going to be equal. And that's because of this plus and minus. Whatever you get under here, you're going to have a plus and a minus, which means you're going to get two different numbers. But these two complex roots, they're going to be conjugates. So that's something to keep in mind. Okay, so let's just look at, instead of finding the whole root, which we're going to do, I want to just figure out what this is, if we're going to have real roots or complex roots. So what is b squared minus 4ac in this case? Well, b is negative 2. If we square that, we get 4. Subtract 4 times a is 1, and c is 5. So we get 4 minus 20, which is negative 16. So we have a negative number, which tells us we're going to have two complex roots. Okay, and when we graph this, we know that it's not going to go through this x-axis. Now let's find the roots. Just make some room here. Okay, so our roots are x is equal to negative b plus minus square root. We've already simplified this. This is negative 16 over 2 times a, which a is 1. So this is 2 plus or minus. Notice that the square root of negative 16 is the same thing as the square root of 16 times the square root of negative 1. Just breaking it into two pieces. And this is 4, because this is a perfect square. And this is I. So we get 2 plus or minus 4i over 2. Let me write it down here. Now, all of this has a common factor. Everything is divisible by 2. So we get x is equal to 1 plus or minus 2i, which tells me x is equal to 1 plus 2i, and x is equal to 1 minus 2i. Those are our complex roots. How do we graph this? Well, there's several ways to graph this. We can put it in the form, could write it on the side. So now that we have all of this done, I'm going to erase this. Now we have to go back to what we did a section or two ago. So to graph this, we can put it in the form f of x is equal to a x minus h squared plus k, where hk is the vertex. We could also just find the vertex, graph it, find the axis of symmetry, find an additional point, and that's basically all we have to do, and just figure out if the graph is pointing up or down. So our function here, if I erase this piece, let's look at the original function. It's x squared minus 2x plus 5. This number in the front is 1, which tells me the graph is pointing upwards. Let's find the vertex. The vertex is h comma k, where h is negative b over 2a. Let's find that really quickly. So 2 over 2 times 1, which is 2 over 2, which is 1. And k is equal to f of this negative b over 2a. So we're just plugging 1 into the function, which is 1 squared minus 2 times 1 plus 5, which is 1 minus 2 plus 5, which is negative 1 plus 5, which is 4. Okay, so the vertex is 1, 4. Let's graph that. Here's 1, we go up 4. The graph is pointing upwards. I'm just going to do a sketch. It's going to look something like this, but if I want to be very careful, I want a good sketch, I need to at least find one more point. The axis of symmetry is right here at 1. What I could do is I could find the y-intercept. So let me erase this. We could find the y-intercept. That'll help us graph this. That means we set x equal to 0. If you put 0 in here, you'll get that h of 0 is equal to 0 squared minus 0 plus 5, which is 5, which tells us that we go through 0, 5, which I've already put here, and then that would mean we'd go through this point on this side as well. So that would give us a better sketch of the graph. And you can see we don't cross the x-axis at all. Okay, so we're done with this problem. Also, if we wanted to use transformations of functions, I've gone through this. I don't want to really do too much of this, but I want to just remind you that we can write this way. So we would say a here is the number in the front, which is 1 times x minus 0 squared plus 5, which tells us that we don't move left or right because we have a 0 here, and we move up 5. Why did yeah, I think I erased this was a 1, I'm sorry. I was getting confused with this point here. Now the vertex we found was 1, 4. So it would look like this. Sorry about that. The vertex is 1, 4, which tells us we would move to the right 1 unit and up 4 units. This is the y-intercept, which helped us graph this. Okay, moving on. I have k of x is negative 2 x minus 4 squared. We want to determine the character of the x-intercepts. Figure out if we have complex roots or not. We want to graph this, and we want to find the roots. So the first thing I'm going to do is set it equal to 0. I can divide both sides by negative 2. And then what can I do from here? Notice I have something squared is equal to 0. Well, this is not a negative number, which tells me I'm not going to have any complex roots. So I'm either going to have one real root, or 2 real roots. Take the square root of both sides. Plus or minus 0 is just 0. And we get x is 4. Notice that I get 1 real root, and we already found it. It just shows up twice. And you can see it shows up twice because I have x minus 4 squared. So when I factored this, I have 2 of these. So x minus 4 times an x minus 4, which tells me that this 1 real root, when I factored, it showed up twice. Okay, let's graph this. We have the root. Let's put that root here. So x is 4. Remember, it's the x-intercept, so it goes through 4. This graph is pointing downward. The a here, because this is in the form k of x, is a mod squared plus k, where this h is 4, this k is 0, this a is -2, which tells me I'm pointing downward. And remember I said that if we have one real root, it lays on the, it's the vertex and it lays on the x-axis. So we're pointing down like this. We can be more careful by finding another point. You can do that. I'm just going to move on because we've discussed before. But you could find one point, maybe the y-intercept, and that can help you draw this graph. But this is the idea of what it looks like.